Hi, this video is going to be about this volumetric sequence of Cuboctahedra unknown form, Icosahedron Cuboctahedra, not based on using the S factor, but by using just phi. So what we have here is a Cuboctahedron that I've just highlighted one face, and then we have larger than that an Icosahedron that completely surrounds the cuboctahedron. And then lastly, we have a cuboctahedron that surrounds the icosahedron. The six of the icosahedron's edges are on the same plane as the cuboctahedron, the larger one. So the smaller cuboctahedron, which I'll get to in a second, I just want to show this line. Oh boy. You'd think you could hit the right marks. Okay. So there is the edge of that icosahedron. See how it's on the plane with the square face of the cuboctahedron. Okay, now I'm going to remove the icosahedron skin as well and talk about the edge lengths real quickly. The edge length of this inner cuboctahedron from here to here is going to be, whatever it does that, I hate it. Hate it. Okay, I want to do this. That edge length there that I highlighted is going to be square root of 2. Okay, then the edge of the icosahedron is going to be 2. And the larger cuboctahedron edge is going to be square root of 2 times phi. So that means that the cuboctahedron on the inside is phi, the larger one is phi greater. It's been increased by phi on all the edges, so it's phi to the third larger in volume. The cuboctahedron, that's the smaller one that I'm working on now, has a volume of 7.07, I have it written down here, 7.071067, which is really just 5 times the square root of 2. Then the icosahedron's volume is 5 times the square root of 2 times phi to the second power, which is 18.51229. There's a method to my madness here, I hope. Anyway, I probably shouldn't even have done it that way, but I wanted to show that this ray from the center here to the outer corner for the larger cuboctahedron, that distance there is square root of 2 times phi. Whereas this edge here, which is, I mean, the edge and the, because it's a vector equilibrium, the edge and the radial lengths are the same. This edge here is from this point here to this point, it's just square root of 2 from here to here. Okay, I want to undo all that activity. You got to see the inside there. Bring me back my kid. Okay, so now I'm just going to show the radius coming through here. Then I'm going to find the midway point. It says start midway point. Okay, so I have the midway point, and I'll put a few more. Whoops. Really hating myself today. Really getting bugged. Okay, that kind of stuff. All right, here we go. All right, and then we want to go here to here, and we want to do the last one here to here. Okay, now I don't know why I did all that either. Let's just put all that around. Now we have all those radius. Now I found the midway point. So if this is the square root of 2 from the origin to this point, and it's square root of 2 times phi from the origin to this point, it's actually the distance from here to the origin is phi squared times the square root of 2 over 2. That distance may be familiar to some of you as being 1.85 0.1229, which is 1/10 the volume of the icosahedron. But we're talking about an edge length. So nonetheless, which means then that I am going to build yet another cuboctahedron. Messed it up. Oh, I hate it when I mess up. I don't know what I did wrong. Okay. Okay, we'll do this. And hopefully it won't give me all that extra stuff, and it is. I don't want those cross lines. Yeah, I don't know why it's doing that. It's not behaving. I didn't know I put those cross lines in there. Maybe I did. Oh, I did that wrong, is what I did. It was interesting though, but I did do it wrong. I meant to go cuboctahedron square face. I wanted to put the edges in first. And then I wanted to make a cuboctahedron, which I did this time. So now we actually have 3 cuboctahedra. It gets kind of hard to see. So then we can take one of the 4 hexagons that slice through the cuboctahedron. And I knew I had clicked the wrong edge by a long shot. It's really not behaving. It's just because I'm trying to rush here. This is just something I want to share with you guys because it's cool. It's intriguing to me anyway. What I consider cool is not what a lot of other people consider cool. Okay. So we got a hexagonal plane. Well, let's put all 4 of them in. Okay, now we can see like a tunnel now in here. This is where it gets cool. You can see the blue icosahedron. There's a central cuboctahedron, then there's a cuboctahedron that's exactly at the midpoint between the 2 other cuboctahedra. One other thing I should have shown, and you can kind of see it from here, is that the distance between, well, that's kind of what I was showing, the outer 2 and the icosahedron is also halfway, which tells me that that cuboctahedron I just generated between the 2 other ones is actually what we call the small guy cuboctahedron. And we have been discussing that various times, and it's kind of interesting. Its volume is 15.860645, and we found if we multiply that volume by twice the S factor, we get the icosahedron, and then if we multiply it again by that S factor, we get yet another cuboctahedron with edge 2 from the jitterbug process. Okay, now I talked about how the central cuboctahedron is midway between the inner and outer octahedra that I first described. Thought I lost the recording. Anyway, what I'm getting at is there is a midway point of the central cuboctahedron, and then it lines up with the face of the icosahedron. What's also interesting is that these edges of the icosahedron and that central or small guy cuboctahedron are crossing at a midpoint. I'll try to get them all in there. Oops. Well, this is not working out. It's the ability to hit the click on the spot, you know. Some days are better than others. Okay. Now I believe I have them all there. So what is fascinating to me, I'll have this one. That is interesting. Okay. I could have done it that way. Alright, I could have just done icosahedral symmetry and got them all. Okay, so they're midway cuts, so that means you can get 4 triangles out of 1 because they're all half the original edge. So these are all 1 edge triangles, and there we have them all over. Now what's fascinating to me is that they sit just perfectly inside of not only the 8 tetrahedral spots, but 2 of them rest perfectly, or are within the cuboctahedral spot as well. So what we also have here is the makings of a icosahedron, the dual of the rhombic tricotahedron. Um, it has a volume. I don't know the number. I should just have the number, but I don't have that. But I know it's 79 and 17 E modules, 79E and I hope I'm saying that right. Anyway, 79 and 17 are the two adjoining E module values. So it's kind of a rough video because I just figured this out, but I find it rather fascinating that the triangles, the center of 4 triangles is also lined up with the center of this triangle here that goes with the cuboctahedron. And I'll just show you the icosahedron here. So you can kind of see there's the icosahedron. It almost looks like these are bent downward, but they're not. It's just an optical illusion. That is a plane. So there's your 2 frequency icosahedron, but it's really just a volume 18.51 icosahedron with the edges halved, creating 4 triangles per face. And that is it for now.